In section 2.2, we'll talk about what is the limit of the functions, and we'll learn how to find limits graphically and numerically. Definition of limits. So the limit is a value to which a function approaches to as the input approaches to the same real value from either sides. If you look at this graph right here, so the function, this is the graph of the function f of x. And if you want to find the limit of this function f of x when x goes to 2, you have to look at the values, the value at which the functions both approaches to from both sides. And in this case, that value is 3/2. You see that the functions from the left approaches to 3/2, and the function from the right approaches to 3/2. So the limits of the functions f of x when x goes to 2 is 3/2. So how we can find the limits? The very first technique that helps us to find limits of the functions is using this graph. So for an example, if I want to find the limits of these functions when x goes to 0, how can I determine that limit? So if you can graph the functions, you can see it right away. This purple graph right here is the graph of the functions x times sine of x. And you see that as x goes to 0 from the left, the function values go to 0 from the left. And as x goes to 0 from the right, the function values goes to 0 from the right. That means the limit of this function when x goes to 0 should be 0. Using graph, right? Now, if you don't know how to graph these functions or you don't have any access to its graph, then you can use table values to compute the limit numerically. How can you use a table values? As we know that limit is the values, is the y values, which the functions is approaches to from both sides of the x value. And the x value that we are looking at is x equal to 0. So I pick a few values on the right side of 0 and a few values on the left side of 0. And in order to have a good estimation, I pick points or values from the right side or from the left side that are very, very close to 0. Which is 0.001, 0.001, 0.01, and so on and so forth. And by picking these values, I can find the function values, and then from the function values of all this value, I will try to find the patterns so that I can make an estimations for the limit of the function when x goes to 0. So if x equals to 0.001, if I go to decimal and I use these functions here, so this was 0. So there's three zeros, and you get 9.99 times 10 to the 9, so it's very, very close to 0. If you decrease one of the 0, so it goes up to 10 to the -7, right? And if you get rid another 0, so it's go up to 9.99 times 10 to the -5. And this functions is a symmetrical functions, which means if you flip the right over the y-axis, you get to the left of the functions. That means if you get rid of this negative here, you will get the same as the positive values. So I go to my tables and I can put in here. So 9.99, right, times 10 to the 9, negative 9, 9.99 times 10 to the negative 7, 9.99 times 10 to the negative 5. And symmetrically, I would have 5.99 times 10 to the negative 9, 9.99 times 10 to the negative 7, 9.99 times 10 to the negative 5. Okay, so this is very small number that is very, very close to 0. And the pattern is from the left, the further left is bigger, so it's decreasing here. And from the further right is also decreasing here. And from both sides, the function values f of x both meet at 0. So that means the limit of x sine of x when x goes to 0 is 0, which is the same as the result that we found using the graph. Next, we do the first example. If we consider the functions, this is the piecewise functions. So the y value is equals to 1 when x is different to 2, and the y value equals to 0 when x is equals to 2. Find the limit of the functions when x goes to 2. So before we can find these limits, maybe it's worth it to graph the functions. The functions is x and y, right? When x equals to 2 here. So then 1 should be here. Okay, I'm gonna use a different color. And the function, it just equals to 1, right? When x is not 2. And when x is 2, the function should be equals to 0 right here. And if you look at this graph of function f of x, what is the limit of this function when x goes to 2? So the limits again is a point where the function approaches 2 from both sides. Okay. And it looks to me that the function is approaches to 1 from both sides, even though the function values equals to 0 when x equals 2. So this is a good example that shows you the limit of the functions is not the same, it's not always the same as the function values when x equals to 2. All right. And now we can discuss the 3 common types of behavior that are associated with non-existence of a limit. Let's go to the first example. So this example shows you the different behavior, right? The behavior that are different from the right and from the left. So this is the graph of these functions right here. And you can see that when x goes to 2, the left side of the function goes to -1, and the right side of the functions go to 1. So they go into different points. That means the limit of this function when x goes to 2 doesn't exist. All right. The next example, the unbounded behavior. If you look at the function tangent of x, what happens when x goes to pi over 2? So when x goes to pi over 2 from the left side, the function values go up to positive infinity. And when the values goes to pi over 2 from the right, the functions goes down to negative infinity. So they go into different ways, unbounded values. That means the limit of these functions here is undefined. All right, let's look at the last example. When you have an oscillating behavior, So this is the graph of sine of 1 over x, and you can see that the function is oscillating rapidly here around x equals to 0. That means we cannot locate if there's any point where the function approaches to the same point from the left and from the right. So the limits of these functions here when x goes to 0 is also undefined, doesn't exist. All right, and if we look at these 3 examples, there's a common characteristic that these 3 examples share, which are each of these functions here has a denominator. So if you have if your function has a denominator, if your function is in the rational form, then the function will be undefined at some point where the denominator equals to 0, right? So tangent of x equals to what? Sine of x over cosine of x. Okay. 2 is a point where the function is undefined. 0, pi over 2 is a point where this function is undefined. Pi over 2 is a point where cosine equals to 0. And then 0, when x equals 0, the function is undefined. Okay, so we can see that all of these functions are in a rational form. So the limit doesn't exist. Limits do not exist at point where those functions are undefined. So this is the first exercise. This exercise asks you to find the limits of this function when x goes to 2 numerically. That means you have to use a table of values. So you can create tables of x values and y values here, right? So x values are the values that are close to 2 from the left and close to 2 from the right. And I pick 3 values from the left and 3 values from the right. And I compute the function values when x equals 1.9, 1.99, 1.99, and so on and so forth. So after gathering all the function values, I make an observations, which is, it started from a bigger values, and it's decreasing down to 0.5. Okay. So it goes from bigger values and goes down at x goes to 1.99. And from the right side, we start at a smaller value. This is smaller value and it keeps going up. And also it stopped at around 0.5. So the answer for this limit should be 0.5 is the answer. And when x equals to 2, the function is undefined. So you have doesn't exist. So the function value when x equals to 2 doesn't exist. And from both sides, left and right, functions approach to 0.5. Okay. If you want to look at the graph, so it should be, this is the graph of functions. ln x minus ln 2 parenthesis divided by x minus 2. Okay, so this is the graph of these functions. And you see right away that when x goes to 2, here from the left, the function's decreasing down to 0.5, and x goes to 2 from the right, the function increasing up to 0.5, and they meet at 0.5, even though the function values when x equals to 2 is undefined. All right, next exercise. So this exercise gives you a piecewise functions and asks you first sketch the graph, and then second identify the values of c for which the limit of these functions here exist. So this is the graph that I came up with. So the black graph here is a graph of sine of x, and you only take sine of x when x less than 0. When x from 0 to pi over here, then you take the graph of 1 minus cosine of x. You can start with cosine of x, flip it over the x-axis, and then move it up by 1 to get this graph. And then from pi to positive infinity here, you would take the graph of cosine of x. So this is the portion of cosine of x started at x equals to pi. If you look at this graph of these functions, most of the points on the number lines, the functions, the limits of the function exists, right? Except this point right here, when x equals to pi. So except when x equals to pi, the function f of x is not the limit of the function of x when x goes to pi, let's say. The limit of the function f of x when x goes to pi equals to, do you have the limit? So when x goes to pi from the left, the function approaches to 2, right? And when x goes to pi from the right, the function approaches to -1. 2 and -1 are the two different values. That means the function of this, the limit of this function when x goes to pi doesn't exist. And you can conclude that the limit of the function when x goes to any point that's not pi exists everywhere else. Okay, based on the graph that you just made.